AIDS in 2009. And if you just take their data and you plot the number of infections per year against the logarithm of the viral load, we see that the maximum rate of transmission is about 10% a year, which is about what Slim Abdul Karim found in his microbicide trial. This is a log scale, so this is 100,000, 10,000, 100,000, and a million. And we can see that as viral load increases, there's no question that transmission increases. But the precise pattern is difficult to say. I mean, it certainly looks as if there's a more rapid increase at the beginning and a leveling off. And what most of us do with data like that is we fit it to a power law function. So a power law gives you a linear fit on a log-log scale. So this is the conventional way of analyzing those data. And all of those data sets have been analyzed in this way. And what this tells us is that if we start off at a viral load of about 10 to the 5, 100,000, and we reduce it to about 100, we get about a 10-fold reduction in transmission. I prefer to use a different model. I prefer to use a model where we assume that at low viral loads, transmission is proportional to viral load. That seems to me to make biological sense. If you low viral load, if you have twice as many viruses, you're twice as likely to get infected. We still have some kind of saturation effect here, and I've asked all the molecular people I know what could possibly lead to the saturation, and none of them have any answers. But it seems to me to be fairly clear, and all of these data sets show the same effect. But the point is that if we use this model instead of that model and fitting it to the same data, we see that if this is how it works, then reducing viral load from 100,000 to 100 gives you a 100-fold reduction in transmission. So we go from 10-fold here to 100-fold here. So it's very important to understand what is the nature of the relationship between viral load and transmission, not just that it goes up, but precisely how does it go up and why it goes up. And this is really a question for the virologists and immunologists and the cell biologists, and maybe they can help us to understand that. The other thing we need to know if we're going to think about what the impact of antiretroviral therapy might be on transmission is what is the viral load in people before they start antiretroviral therapy. And there are very few published data on this. One set of data, which I got from Bertrand Auvert, sorry about the spelling mistake, from his study in Orange Farm, was this. He took blood from a few thousand young men, and he measured their viral loads. And what he found was enormous variation, so the viral loads vary from less than 100 to more than 1 million, with a median around 50,000. But what this tells us immediately is that if, as some people have suggested, you were to say, let us use viral load testing in order to decide who to start an antiretroviral therapy, and if you set the limit at 50,000, you'd get about half of the people who are HIV positive. Now, of course, the people on the right of the graph are more infectious than the people on the left of the graph, so you're doing a little better than that. But you're only going to reduce transmission by something like a factor of 2, which again still doesn't get us anywhere close to where we want to be. But we want to estimate that number rather more precisely. So I'm going to show you a graph which looks rather complicated. It's not really, but I'll try and take you through it slowly. So what I've done is I've taken these two models. On the left-hand side is the conventional model where you do a power law fit. On the right-hand side is my model where you assume a linear increase followed by saturation. The numbers on the graph show you the reduction in transmission. So this reduces transmission by 2, 4, 8, or 16 times. In my model, the reduction is greater, so 2, 4, 8, 16, up to 128 times. So the numbers in the circles tell you by how much do you reduce transmission under different conditions. The vertical axis is the threshold viral load at which you start antiretroviral therapy. The horizontal axis is the viral load you get when people are on ART. So you might, for example, start at a viral, say, well, we're going to put everybody above 10 to the 5 on therapy. We might then say we think we can reduce viral load to 100. And if you do that on the conventional model, you'd get a 2-fold reduction in transmission, and indeed on my model, you'd get about the same. But just to be more explicit, if you started, the blue dot there corresponds to a situation where you put everybody above 50,000 onto antiretroviral therapy, so this is 50,000 on a log scale, and we assume that we can reduce viral load to an average of about 400 when people are on therapy, so this corresponds to 400 on a log scale. And what it tells you is with the conventional model, you'd get about a 3-fold reduction in transmission, and in my model, you'd get about a 3-fold reduction as well. So in either model, if you start at 50,000, you reduce to 400, you're going to reduce transmission by a factor of 3, which is important and very significant. It's greater than you get from either microbicides or male circumcision or PrEP taken orally. but it's not enough to eliminate transmission. To eliminate transmission, you really want to get down to at least a situation where you're starting at about a viral load of about 10,000, and then you want to suppress the viral load to 100 or less. And if you can do that, then on the previous model, you'd get about a 6-fold reduction in transmission. On my model, you'd get about a 16-fold reduction in transmission. So that's looking better. What you would really like to do is just start everybody immediately. Because if you start everybody immediately, then even on the more conservative model, you're going to reduce transmission by a factor of 8, which is roughly where we want to be. On the model that I'm proposing, we would reduce transmission by a factor of about 100, which is much better. But either way, if we start people on antiretroviral therapy immediately, irrespective of viral load, and we can sustain a reduction to about 100, then we're in business. Okay, the other big question, of course, which all of us ask is, what does ART do for TB? Because the most common opportunistic infection associated with HIV is TB. So how are we going to stop HIV-associated TB? Well, again, the data are not what they should be, and we would like to get much better data. Quite a lot of these data from Robin Wood's group in Masiphumelele. But this is a whole series of different studies in which they've measured the incident rate ratio for TB for people on and off ART. So these are all the studies from South Africa, Europe, Brazil, Italy, Spain, and the United States. And what you see is that first of all, the error bars are very big, so the studies are not very precise. There's an awful lot of scatter on the points, which may depend on the CD4 cell count or the viral load or something else when the study was done. But our best guess, at least, is that overall the incident rate ratio is about 0.4. So putting people onto antiretroviral therapy should reduce their risk of getting TB by about 60%, averaged over the whole range of possibilities. So in the short term, we can be fairly confident that if we roll out antiretroviral therapy treatment as prevention, it has the potential to reduce the incidence of TB in HIV-positive people by about 60%. In the long term, of course, the only way we're really going to get rid of HIV-associated TB is by getting rid of HIV. So in the short term, we can get a 60% reduction, which is very important. We can reach the current WHO target of halving deaths in HIV-associated TB by 2015. In the long term, it all depends on what we do to HIV. But that's all the very simple stuff. That's all essentially the sort of static modeling. And if we really want to get an understanding of what's going on and how it's going to change over time, we have to do dynamical models. And dynamical models, of course, by definition, are much more complicated. But the easy part on HIV is the basic structure. AIDS is actually a very simple disease from a modeling point of view. It's much easier to model in TB or many other diseases. You have susceptible people, infected people, they may or not get ART and then they die. So that's all you have to really think about. The difficult part is getting reliable data on sexual behavior and especially the structure of sexual networks, which I'm convinced is really the key to understanding why it is that in 500 million people in the whole of North India, prevalence is less than 0.1%, and why it is that in South Africa, prevalence is 20%. So we've got a 200-fold difference in infection rates in South Africa and North India, and nobody can put their hands in their heart and say they can explain that. But I think those are the kind of